In this chapter, I will discuss refraction of light when it passes from one transparent medium into another. I will also discuss how lenses refract light and the lens equation. When light strikes a transparent material, it usually changes direction. This property is known as refraction and is the reason for many applications in imaging, lasers, and telecommunications. The refraction of light can be studied by looking at the path of light rays as they pass from one medium into another. To be able to quantify refraction, let's first introduce some parameters and terminology. Let's consider two media that are in contact with each other. Medium 1 and medium 2. The straight line here represents the boundary between the two media. Examples of two media that are in contact with each other would be air, water, or water, glass, or any other combination of materials. Let's also draw an imaginary line that is perpendicular to the boundary between the two media. This imaginary line is called the normal to the boundary. Now let's look at the path of a light ray that is coming from medium 1 and passes into medium 2. So here is the incident light ray. The incident light ray makes an angle theta I, which is the angle of incidence with the normal to the boundary. And when the ray passes into the second medium, it is going to travel along a different direction, which means that it will make a different angle with the normal. And this angle I will call theta r, or angle of refraction. So theta I is the angle of incidence, and theta r is the angle of refraction. When light rays enter another medium, they change direction. The extent to which light bends in the second medium is determined by the optical properties of that medium. The index of refraction determines the amount of bending of light. So the index of refraction, which we label with n, varies with each medium. Larger index of refraction equals more optically dense medium. Here are some values for the index of refraction for some common substances. The index of refraction for water is 1.33. The index of refraction for glass varies from 1.5 to 1.9 depending on the type of glass. The index of refraction of air is 1. The index of refraction for vacuum also 1. So what does optically more dense medium or less dense medium mean in terms of the value of the index of refraction? So air is less optically dense than glass or water, which have larger indices of refraction. And then if you compare glass to water, glass is more optically dense than water because it has larger index of refraction. And so if you obviously visualize what glass is and what water is, you can tell that glass is denser by its physical properties than water. And so this, in a way, translates to the index of refraction. So to summarize, the index of refraction determines the amount of refraction light experiences when it enters a different medium. Since the index of refraction determines the amount of refraction of light, the angle of incidence, the angle of refraction, and the index of refraction of each medium are related. And this relationship is given by Snell's law. So here is my setup. We have two media, medium 1 and medium 2, with indices of refraction N1 and N2 respectively. This is the boundary between the two media. This is the imaginary normal to the boundary line. And so here is my incident light ray, which makes an angle of incidence theta I with the normal. After the light ray passes into medium number 2, it changes direction because of refraction. And now the angle that it makes with the normal is the angle of refraction theta r. So Snell's law gives me the relationship between the two angles and the indices of refraction. So Snell's law reads that the product of the index of refraction and the sine of the angle of incidence for the first medium is equal to the product of the index of refraction and the sine of the angle of refraction in the second medium. This applies for any two media with indices of refraction n1 and n2, and for any set of angles of incidence and refraction. So from here, you could find any of the four quantities if you needed to. You can find any of the indices of refraction or any of the two angles. Here again, n1 is the index of refraction of the medium from which light is incident. Theta I is the angle of incidence. N2 is the index of refraction of the medium in which light refracts, and theta r is the angle of refraction. Now let's see how the indices of refraction of the two media affect the angle of refraction when light passes in the second medium. So first let's consider the two media with indices of refraction n1 and n2, where n1 is less than n2, which means that the second medium here has higher optical density than the first medium. For example, the first medium could be air, and this could be either glass or water. In this case, the angle of refraction will be smaller than the angle of incidence. Or in other words, the light ray, once it passes in the second medium, bends towards the normal. So one more time, when the index of refraction of the second medium is larger than the index of refraction of the first medium, the angle of incidence is larger than the angle of refraction. Or the light ray entering the second medium is going to bend towards the normal. The other possibility is that the first medium has larger index of refraction compared to the second medium. So the first medium is optically more dense than the second medium. Think about it as, for example, this being glass and this being water, or this being glass or water and this being air. In this case, the refracted ray is going to bend away from the normal. So the incident ray makes an angle theta incidence with the normal. Once it enters the second medium, it's going to bend away from the normal at an angle theta of refraction, which is larger than the angle of incidence. So when the index of refraction n2 is less than the index of refraction of the first medium n1, the light ray will bend away from the normal, or in other words, the angle of incidence is smaller than the angle of refraction. Now let's see how light refracts when it passes from medium with index of refraction n1 to a medium with index of refraction n2, and then back into medium with index of refraction n1. For example, this could be a situation where we have transition from air into glass and then back in air. So I'm going to apply the basic rules that I discussed already for each boundary here and here. Let's also consider the following relationship between the indices of refraction. N1 is smaller than N2, which means that This medium here is more optically dense. As I said, if this is air, and air here and here, and this is glass, then we have this case. So here is the incident light ray. This is the normal to the boundary between the two medium. When it enters the more dense medium, the light ray will bend away from the normal. So the angle of refraction theta 2 will be larger than theta 1. Let's write this down. Now let's see what happens when the light ray enters back into medium 1 here. So the angle that the light ray in medium 2 makes with the normal is here is also equal to that angle, because we have two parallel lines that are crossed with a line. So this angle here is theta 2. So now theta 2 for this transition here, for this refraction, becomes the incidence angle. And when the light ray enters the medium with index of refraction n1, it's going to bend towards the normal now, because this index of refraction is smaller than that index of refraction. So this angle theta 3 should be the same as the original angle of incidence theta 1. And this is all because all these refractions happen about these parallel lines. So in the end, this light ray and this light ray are parallel to each other, but are shifted a little bit from each other. So this is the effect that is observed when light passes from one medium into another and then back into the first medium. So the angles theta 1 and theta 3 are equal to each other. An interesting effect that is due to the refraction of light is the position of an object that is submerged, let's say, in water, as we are looking at it from above, from air. The position of the object looks to be much closer to the surface than where the object is in reality. So if we have an object that is resting on the bottom of a shallow lake and we look at it from above, from air, due to the refraction of light rays when they enter from air into water and then after reflection from the object come back from water into air, it would appear that the object is actually closer to the surface when it is not. So consider our object at the bottom of the lake. This is the surface of the water, and let's say that we are looking at the object from above. So here is an incident ray. It refracts into the water. It reflects from the object, refracts back in air. So from the behavior of light rays as they move between media with different indices of refraction, it follows that when the light ray enters into water, it's going to bend towards the normal. After reflection, when it enters back in air, it's going to bend away from the normal. So this is the real picture of how the light rays travel. What does the eye see? For the eye, it appears as if the light rays are simply going on a straight line as they enter into the second medium, or in other words, there is no refraction. And then after reflection from the apparent position of the object, they come out of the water, again without refraction. The reason for that is that the human brain does not understand the concept of refraction, or in other words, we don't see it. So to us, to our eyes, it looks like as if the rays are just traveling along a straight line all the time. And so, to us, the position of the object is right here, while in reality, it's on the bottom. So the amount of refraction depends on the angle of incidence. For example, if the incident light ray is perpendicular to the boundary between the two media, air and glass, then the light ray is going to go straight through the second medium and back into the first medium without any refraction. But if we start to increase the angle of incidence, for example like here, then we see how the light ray is making a larger angle of incidence in the first medium compared to the angle of refraction in the second medium. So less optically dense medium, more optically dense medium, which means that the index of refraction N1 is less than N2. And so as a result, the light ray bends towards the normal in the second medium. If we keep on increasing the angle of incidence, for example like here, then the angle of refraction of course will also increase, but still it will be smaller than the angle of incidence. But here now we can see how the exit light ray here back in the first medium is, as I explained before, parallel to the incident, but it's shifted a little bit. Finally, if the angle of incidence is large enough, we are going to start to see some reflection from the boundary between the first and the second medium, like shown here. An interesting effect can be achieved when we have light traveling from a medium with higher optical density, such as glass, and it refracts into a medium with smaller optical density, such as air. So if the incident ray makes a incident angle with the normal to the boundary that passes certain value, experimentally was observed that the light ray does not continue to propagate in the second medium. It will reflect from the boundary between the two surfaces, like shown here. So for this to be achieved, the angle of incidence here must have a certain critical value, past which we are going to observe this reflection from the boundary between the two media. So this is known as the critical angle, and this effect is known as total internal reflection. So here is the setup. We have two different media, one with index of refraction N1 and one with index of refraction N2, and N1 is bigger than N2. So for example, this could be glass and this is air. So then we have an incident light ray that is coming from the glass and we want to send it into the air. Well, if the angle of incidence is equal or larger than a certain value which is known as the critical angle, this light ray is not going to refract into the second medium. Instead, it's going to reflect from the boundary back into the first medium. When the incidence angle is exactly equal to the critical angle, then the reflected light ray will be actually traveling parallel to the boundary between the two media. And when the angle of incidence is larger than the critical angle, then we have total internal reflection. This property of refraction between media like that is actually very useful in telecommunications. So if you consider a piece of optics fiber, which is essentially made from silicon on the inside, I can send a signal consisting of light rays, which are going to propagate inside the optical fiber due to total internal reflection. So when a light ray hits the boundary between the fiber and air, it's going to reflect, and then it's going to reflect again, and again, and again, and again, and again, and so on and so forth. And so this is a way to carry information with the speed of light without much loss over gigantic distances. And since the possibility to transfer information here is limitless, since I can fit many different light rays here that carry information, this is right now probably the most efficient way to carry information.